Okay, so now that we have worked our way all the way through the various ins and outs of ARIMA modeling, I know we've done kind of bits and pieces of all of this stuff, but I thought I would go ahead and tie it together with kind of one example from start to finish. I'll show you a few things, especially towards the end, that I don't believe we've talked about yet. Perhaps maybe most importantly, this idea of something called ensemble modeling or ensemble forecasting. Okay, so let's buckle up and get going. Put your put your tray in the upright and something another position. All right, yeah. So here we are. There's an airlines data set. I believe it's real data. It's been years since I inherited it. You should be able to find it on D2L. It's monthly data, and it measures passenger totals. These are in units of thousands of passengers. In international travel, I think for a certain airline company, over an 11-year period. So we have whatever 11 times 12 number of observations. 11 years worth of monthly observations. And our goal is to build a suitable, possibly seasonal ARIMA model because we have monthly data. So we need to consider at least the possibility of seasonality. So let's go ahead and do that. All right, so here's our data set, right? It's a very, very, very clear-cut seasonal pattern, right? In fact, to be honest, I see a data set like this, and this looks to me like a really great data set for using seasonal decomposition. That said, our goal today is to practice our seasonal ARIMA skills. I see a clear upward trend, right? That is, as time's going on, we're tending to see more and more international travelers or international passengers. And then we also see this kind of seasonality, these seasonal peaks. Little hard to look at, and actually, to be honest, I started arbitrarily at January 1960, so that first observation might not even be January. So maybe a little bit wary doing too much interpretation. My guess is, and maybe a lot of times the data does line up at January. It does look like maybe those peaks are happening around the summer, which is when I would anticipate them to happen. So what's the first thing we need to do? The first thing we need to do is we need to make sure that we have stationary data, right? We need to make sure that our data is fluctuating around a common mean with a constant variance. That's certainly not the case now, right? Instead, we see this global upward linear trend, and we see increasing seasonal variation. So we need to take care of that. Yeah, all right. Very clear linear increase, very clear seasonal pattern with increasing seasonal variation. So let's go ahead and see what we might need to do. So here's our first attempt, right? Again, most common way to achieve stationarity is by doing various differences. This is the first simple difference. It's always a little bit tricky to see, like, sometimes these seasonal patterns, but I feel like I do still see that seasonal pattern, except now it's kind of spiking downwards instead of spiking upwards. I very clearly see that the variance is not constant, right? I can see very clearly that I still have this increasing variance, which does violate this idea of stationarity. So the first simple difference by itself is not sufficient. Now, it's tempting to just add a seasonal difference on top of this, but I would encourage our next step to be to look at a seasonal difference just by itself, because sometimes that will work, and then that's a overall sort of more parsimonious model. So here's the first seasonal difference. It kind of looks a little wonky, right? That is, it looks like there's like an upward trend, and then it's kind of flat for a little bit, then a downward trend, then an upward trend. So the seasonal difference has maybe removed the seasonal pattern, but I still kind of have these like up and down trends in my data. So that violates this idea of fluctuating around a common mean. So the first seasonal difference is not sufficient to achieve stationarity. So what are we going to do next? What we're going to do next is we're going to look at a combination of a simple difference and a seasonal difference. And there it is, right? And that overall looks pretty good to me. Right, there's that one spike. Yeah, I guess maybe 3 spikes, right? There's a spike. It's like a downward spike towards the end of our time series, and there's maybe 2 kind of like high upward spikes kind of towards the earlier part of our series. But again, these are like 3 points out of whatever 12 times 11 is. I guess we lose a few points with our differencing, but right, more than 120-ish points. We got like maybe 3 little kind of quirks or anomalies, but the bulk of the data seems like it's fluctuating along a straight line. Seems like the bulk of the data has a reasonably constant variance. So I feel pretty good about where we're at now. All right. So next step, what's the next step? Exactly. The next step is we need to now look at our SAC and our SPAC and try to actually use that. Well, we use it for a couple things. One, we can confirm that we do in fact have stationary data, right? Because we say that one of the things we want to see is we want to see that SAC dying down reasonably quickly. And if that SAC's not dying down quickly, that's a sign that we do not have stationarity. So we can look at the SAC to kind of verify like kind of what we've already ascertained with our eyeballs. It's like a second check for us. But maybe most importantly, we're going to use that SAC and SPAC to pick our model. Oh, so here we are. Yeah, a simple difference does not seem sufficient. There's an obvious violation of the constant variance in that case. The seasonal difference didn't seem sufficient as there were sort of alternating periods of upwards and downwards drifting. But the combination of the two, right, seems to get the job done. Let's get her done. So next step, we're going to look at the SAC and the SPAC. That'll help us determine, I say our model, but we're kind of like, we're thinking of our model as having sort of 2 pieces, right? We're going to fit our non-seasonal ARIMA model, and we're going to fit or determine our seasonal ARIMA model. And then, like I said, we can also kind of double check, right, what we've concluded regarding stationarity. All right, so here it is. Here's our SAC and our SPAC. It does look like it dies down reasonably quickly at both the non-seasonal and seasonal level. So I feel pretty good about my previous claim about it being stationary. So maybe look at it for a second. You can pause the video if you want to. Maybe write down on a piece of paper like what you think. Like what do you think the non-seasonal model should be? And what do you think the seasonal model should be? So I'll give you a second. You can pause it. You can write it down. Welcome back. Let's start with the non-seasonal model. So what do I see? I see, right, they got that spike at lag 1. And then they both kind of what? It's hard to say a little bit. Are they both cutting off? Are they both dying down? I mean, both of those second bars are well under the significance line, the red significance line, and sort of stay under there. So I'm going to look at that as they're both cutting off. That said, if you said like I see like especially in that SAC, if you said I see like an oscillating sort of sinusoidal dying down pattern, like yeah, I could see that. I think that would be a reasonable claim. Again, nothing is super clear cut to me, but my heart is telling me, all right, both SAC and SPAC look like they're both cutting off. Now, right, theoretically, there's no model in which they both cut off, so I have to think which one cuts off more and assume the other one's dying down. In this case, it looks to me like the SPAC cuts off more, right? That is the drop from lag 1 to lag 2. It's a larger drop in terms of the SPAC. So I'm going to pick the SPAC as cutting off. then I'm going to assume that the SAC is dying down. I consult my notes, which I did have to do. I admit I don't have this thing memorized yet. Well, I don't know. I feel like I always have it memorized by the end of class, and then I don't teach this class for 2 or 3 years. So when the SAC dies down, the SPAC cuts off. That's an autoregressive model. Here it's cutting off after lag 1. So my thought is an autoregressive model of lag 1. That's what I'm going to put out there. That's my contribution to our discussion. Now, if you said what? If you said they both are dying down, what model would that imply? Maybe pause the video and write down what that would imply if in fact they were both dying down, if that was what we wanted to conclude. You're right. If they're both dying down, that implies a mixed model, and we usually try to do the simplest possible mixed model. So we would try to do a mixed model that's like autoregressive order 1 and moving average order 1. That to me seems like the second most plausible model. We're going to look at it just for like, just kind of for practice. I really don't think that it would be good to say that the SAC cuts off more. I just do not see that. I feel like that's pretty close to objectively wrong. That if I had to say one of them's cutting off more, it does seem pretty straightforward that the SPAC is the one that's cutting off a bit more. Not by a lot, but I think obviously by a bit. That said, if I just didn't feel good about any of these things and I wanted to try, say, a moving average model of order 1, I mean, it wouldn't hurt to look at it. So we're going to see as we move forward, those are going to be the 3, again, we're just looking at non-seasonal models. Those are going to be the 3 non-seasonal models that I'm going to look at. I want to show us how to compare different models. But in my heart, I'm thinking autoregressive order 1, and we'll see how that ends up working out for us. Yeah, so non-seasonal thoughts both seem to cut off, but the SPAC seems to cut off more. If I look back at my notes, that indicates an autoregressive order 1 model, right? Little p equals 1. Other possibilities, right? I guess maybe we could think the SAC cuts off more. If that was the case, we would say moving average model, little q equals 1. Or maybe they're both dying down. I feel that both dying down is maybe a reasonable conclusion. And in that case, we'd have autoregressive 1 and moving average 1. All right, so we have a few possibilities. We'll try fitting all of them. The next thing we need to do is we need to figure out what our seasonal model looks like. So let's go back to that SAC and SPAC. Let's revisit it. All right, so here we are, right? Here's our SAC and SPAC. Now we're looking at what? We're looking for a seasonal model. So the seasonal model means we're looking at lags 12, 24, 36, right? The SAC and SPAC looks a little different this time because I zoomed it out a little bit. So I zoomed it out. I think our previous one only went to 24. I zoomed it out to 36 so I can see basically up to 3 lags, 3 seasonal lags. And what do I see? I actually see for both of them at lag 12, neither of them have a spike, right? They're both significant, or both, sorry, they're both non-significant at lag 12. This is the first lag. So usually when you do not see anything at the first lag, whether it's the first actual lag or the first seasonal lag, that's basically telling you that you don't have like a seasonal model. Now I do have like a little bit of a spike at round about 24 in the SAC. But even then, right, it's just borderline significant. It's like right on, and I'm going to guess even a little under that that red line. So I'm going to guess it's maybe a little bit more than 0.05. And then if we look at lag 36, which is the third seasonal lag, like it's completely gone by then. So I'm actually going to look at that little SAC spike at lag 2 as just kind of like this anomaly. Right? I mean, at seasonal lag 1, it's pretty convincingly close to 0. At seasonal lag 3, it's pretty convincingly close to 0. The SPAC at 24 is you know, it's only halfway to the line, And then the SAC is really just kind of barely touching that line. So my conclusion is going to be, again, maybe erring a little bit on the side of simplicity, that we don't need a seasonal model in this case. Right? Again, we did need to do the seasonal differencing, right? So seasonality still was like important in our model building process. We did have a seasonal pattern, and we had to take a seasonal difference to sort of remove that pattern and achieve stationarity. But after we've done that, we're good to go. We don't need to fit like a seasonal ARIMA model. Yeah, so the SAC is borderline significant at seasonal lag 2, i.e. lag 24, but there's no spikes anywhere else, and so that indicates to me that we're not going to need a seasonal ARIMA model. All right, so we have our model. What are we going to do? Well, we actually we considered 3 possible models, right? And so what I want us to do is I want us to go ahead and fit these 3 models, and we can kind of compare them. How might we compare them? We can actually compare them in a lot of different ways, right? We should be looking at what? At parameter significance, right? The significance of the parameter estimates. We should be looking at LBOC scores. But maybe like the most common metric for like initial comparisons is going to be that BIC, right? That Bayesian information criteria that we talked about. And in that, right, keep in mind, SAS refers to it as the SPIC, the SBC, Schwarz-Bayesian criteria. Okay, so here I am, I'm fitting our first model, right? I went into the model development window, right-clicked in that little white box there, that massive white box, and it gave me the option to fit an ARIMA model, right? So I have to do differencing small d equals 1 and big D equals 1. That does the first simple difference, first seasonal difference. And I'm gonna start with what my heart was telling me. My heart was telling me that we just want an auto-regressive model order 1. Now look kind of in the top right, you'll see like a box. It says root mean squared error. It's grayed out at the moment. Once we fit our model, it'll report that root mean squared error. That's one way of comparing models, right? The smaller the square root of the mean squared error, the better the model. But like we talked about in class, a better metric is going to be that Bayesian information criteria. So we're gonna change that in just a little bit. Yeah, so here we go. I've done all of that. So I fit not just the auto-regressive model. So the topmost model there is my AR order 1. The second model is my MA order 1. And my third model is the mixed model, AR1, MA1. Notice, look in the top right, I've changed that root mean squared error. So you can change it on yours. You click that box. It may not initially give you the Schwarz-Bayesian information criteria option, but if you look, you'll have like a secondary option that says like view all. It only shows you initially like a little subset of things to pick from. But if you click view all, it'll show you like a longer, more comprehensive list, and you can pick the BIC out of that list. Now remember, smaller is better. So here, when I'm comparing these things, they're all reasonably close to one another. But the model that does in fact have the smallest BIC is the one that we had thought from the very beginning, that auto-regressive model order 1, right? So again, it definitely is, it's often not as black and white as we would like it to be when we're using these SACs and SPACs to build our model. And it feels like a little stressful because you're like, I don't know, I just feel like I'm guessing a little bit and I don't want to guess the wrong model. But it doesn't have to be that way, right? Like if you have a couple guesses, or if you're not sure, then all right, then fit 2 or 3 or 4 or 5 models. There's nothing wrong with that. In fact, that's good model building, is to be a little bit open-minded and look at a broad collection of models and then use some criteria like the BIC to narrow it down, which is what we're going to do now. We're going to narrow it down to that autoregressive model. So there we go. As suspected, the AR order 1 model has the smallest BIC, hence is our preferable model. Now, the next thing I want to do now that I've got my model, and there's a few things that we need to do. We still need to kind of look at the model equation, make sure. In this case, we only have one parameter estimate. It's a pretty simple model. We want to make sure that that parameter estimate is significant. We want to check out the L-box scores. But one thing that we've talked about and we haven't really looked at a lot in class is this idea of reliability, right? So we did say that we can measure the reliability of our time series model by holding out some data. Often we like to hold out a year of data, and we can do that in this case. And look at metrics like the mean absolute error or the mean percent error. Both of them are good things to look at. So let's go a little bit closer. I don't know that we've done a full-blown example showing how we do this reliability. So that's kind of what I want to do next. I don't think we've done an example where we really look at like the output and stuff. So let's go ahead and do that. All right. So here I am. Unfortunately, like that little secondary box where it says time range specification kind of obscures what I click on, but underneath that box is like a little button that says set ranges. So I click on the set ranges and it pulls this little box up. All right. And so there's my data, right? 1960 to 1970, 11 years. Notice there's a period of fit and a period of evaluation. So I want to change both of those, and changing one doesn't necessarily change the other. So I want to only fit the first 10 years of data. So that's January 1960 to December 1969. And then I want to evaluate, that is, I want to test my model on January 1970 to December 1970. If I just change those, then like SAS will like automatically kind of change the other stuff. That all right, you're forecasting out 12 periods, and you're actually also holding out 12 periods. Okay. So let's go ahead and take a look. So again, I had to change. Look in the upper right. It says mean absolute error. So I had to change that. I had, before I had it on the Bayesian information criteria because I use that for picking models. Here I want to see how reliable my model is. So I'm going to change it to mean absolute error or mean percent error. I mean, they're both easily fine. In this case, right, mean absolute error is basically saying that we're within 11. On average, our predictions are within 11,000, right? Because we're in units of thousand, within 11,000 of the correct number of passengers for any given month. Okay. So our mean absolute error is at 11.12. Right, where is that coming from? Well, here's like the output for our predictions, right? And so I got January 1970 all the way to December 1970. I could see that column. It's the second column to the right where it says error. That's like my error. Right? In January 1970, there was 360,000 passengers. We predicted there'd be 342-ish passengers. 1,000 passengers. So we were off by about 18,000. So where does that mean absolute error come from? You could verify it yourself if you want to. It's that 18 plus 8 plus 20 plus 8 plus 9 plus positive 17, because we're looking at the mean absolute error, right? That prevents things from canceling out. Plus 15, plus 1, plus 4, plus positive 9, plus 1, plus 16, divide by 12. Put all that into your calculator. Don't round it horrifically like I did. And you'll get that 11 point whatever that we had. Okay? So that's where that mean absolute error is coming from. And then that lets us kind of like, it gives us a nice metric for saying like how well our model works in terms of predicting. And we're predicting for data outside of our model, which helps kind of helps prevent us from, like, say, overfitting a model, right? Making a model that's a little too specialized to the data, and because of that, not generalizing well outside of the data. All right, so there we go. We took a little bit of a closer look at some of the stuff that we've been talking about, the reliability in particular. Next steps, I think, are all things that we've looked at. What would we do? We would check out our parameter estimates, verify that, again, we only have one in this case, but verify that it's significant, right? That our AR1 coefficient is significant. We need to check out our LBOC scores, right? Make sure that they are non-significant, which means that we've modeled the dependency in our data correctly. And in theory, we should look at the correlation matrix between parameter estimates, which we need proc ARIMA to do. We kind of dodge a bullet in this case, but since we only have parameter estimate, there's really no correlations to check. So here's my model equation. SAS picked the no intercept by default. It does that when the intercept's non-significant. So I got a very, very basic model here, actually, right? It's just got one coefficient. That coefficient is, reasonably significant, p-value of almost 0.03. It's less than the usual 0.05 criteria. So everything in my model is significant. That's good. Here are my LBOC scores. They're all well underneath that red line, right? In fact, I can see they're all well, it's a little tricky because we think of as small as saying like below, but really it's above that 0.1 threshold, which is saying that the p-values for all of those bars is more than 0.10. So the LBOC scores look good is our ultimate conclusion, which means that we got a pretty good looking model, right? Pretty simple model in this case. But a lot of times our ARIMA models do end up being simple, and that's nice because we like simple, streamlined, parsimonious models. So yeah, our model's significant. The LBOC scores are non-significant. That's good and gooder. All right. So everything looks good there. If you wanted to ride off in the sunset right now, I wouldn't blame you. However, I want to show us kind of one new thing as we wind down, as we wind the class down, and that is ensemble modeling. So what are ensemble models? Ensemble models, or an ensemble model, is basically a model that blends together other models. And this is typically done with the goal of improving forecasts or predictions, right? In time series, we're dealing with forecasts, but you could also build ensemble models in like a 512 context and use them, for example, to improve your prediction of the weight of a bear, right? That is, you might come up with 3 or 4 512 models and use those 3 or 4 512 models to come up with 3 or 4 different predictions for a bear's weight, and then merge those predictions together into a single prediction, right? That's the idea behind ensemble modeling. And we're essentially doing that. We're essentially doing that by taking the forecast from these different models and creating a weighted combination of them. Okay. Now, to build a good ensemble, theoretically, and this is probably like, this should hopefully be intuitive. We want to use models in which there's low correlation amongst the forecasts. Right? That is, we want to try to use models that are different from one another. Which means what? It means like we started this lecture off by looking at like an AR1 model, MA1 model, and a mixed model, AR1, MA1. Now these models are all very similar to one another, right? And so I would imagine that they're all giving pretty similar forecasts. So building an ensemble with those three models is probably not going to be very effective. Ensemble modeling works best when I'm blending very different methodologies or very different models. So what does that mean for us? Well, one thing that we might do is we might build an ensemble of our seasonal ARIMA model that we just fit, and how about an exponential smoothing model? Right? Two very different types of modeling. And so we can build these two models, which you're doing with your data actually right now. And then how cool is that? I don't have to pick between one or the other, right? I don't have to play a game of Sophie's Choice. I can actually have my cake and eat it too by blending the models together into a single prediction. Wow, how cool is that? Now, unfortunately, we'll see. I think we're okay. So you can see I got my autoregressive model up top. I've added, right here I did exponential smoothing. I picked the multiplicative winter method. Winter method means seasonality. I use a multiplicative model because I saw there was increasing seasonal variation. Notice, well, I still have the mean absolute error up there, so I don't know if that's how I would compare those things. If I really wanted to compare them and try to pick one over the other, I would probably use the BIC. But that's not my goal at this moment. My goal is not to like pick one and boot the other. My goal is to fit these two and blend their forecasts together. And the reason I have that mean absolute error up there is I want to show that blending the models can produce better predictions, right? So the ARIMA model by itself, right, on average is within 11.12 thousand passengers. The exponential smoothing model by itself is within 11.5 thousand passengers. But what if I were to blend these things together? Now, unfortunately, it wasn't working getting a screenshot of this. So I'll just verbalize to you. It's real easy to do in the time series forecasting system, and that is you just right click within that, that big white space in the center of our screen. Right click in there, and it'll pull up a little menu. And one of the options on that menu will be combine forecasts. Okay. And so it gives you, I think, just 2 or 3 options for combining the forecasts. One is to just like use equal weights. And so what would equal weights be? Basically, for any time period, right, it's going to, the new prediction is going to be 1/2 the prediction of the ARIMA model plus 1/2 the prediction of the exponential smoothing model. So there's some other kind of black box approaches where it tries to build like a more optimal weighting system. These black box approaches look at sometimes the root mean squared error. So models that have a little bit of a better root mean squared error get more weight. Or, right, this is what's theoretically preferable. Look at the BIC and assign weights based on the BIC. So whichever one has the smallest BIC gets the largest weight. We talked about this actually, you may or may not remember this. We talked about this idea of ensemble blending when we talked about the IC and the BIC for the first time. Yeah, so here's what when I right click in there and say combine models, this is what I get. I clicked that fit regression weight, and that's what came up with the weights there. So notice it's not quite 0.5, 0.5. It's saying that the ARIMA model, and we did see that the ARIMA model looked a little better in terms of mean absolute error. If we looked at BIC and root mean squared error, I think we'd also see the ARIMA model is a little bit better. Oh, no, I take that back. In this case, it's going the opposite way, right? So I guess I'm wrong. I guess if we were to look at the root mean squared error or the BIC, and this might be, I mean, the data set's posted, so this could be a fun thing for you to do and try to actually do this yourself. Is fit those two models and compare their BICs. What the weights seem to be showing us is that actually the exponential smoothing model has a slightly better root mean squared error or BIC. Not quite sure which one it's using. I had trouble finding that in the time series forecasting help files. So it's giving a little bit more weight to the exponential smoothing prediction, but still pretty close to half and half, right? And so I click OK, and lo and behold, right? That's the beauty of ensemble modeling, right? Instead of using a prediction for my seasonal ARIMA model, instead of using a prediction for my exponential smoothing model, I could use a blended prediction, a weighted prediction, right? That's a combination of the two models. And in this case, it is what? It has improved my predictions. Pretty cool, right? It's improved my predictions by a decent amount, by like 10%. I went from 11.12 and 11.5 to 10.3. It's a pretty nice improvement in reliability. And that right there is at least a glimpse of the power of ensemble modeling. So yeah, so conclusion, using a weighted combination of our two models has improved our reliability. Very cool. And that's all I got for you. So have a great day, or better yet, make a great day.